So for chapter 4, as with a lot of our chapters so far, it's still mostly a review. There's going to be a couple of new things in this chapter finally. We're going to look at stoichiometry, which isn't new, but we're going to talk about an excess reactant. In intro chem, we really focused on the limiting reactant. And now we're going to look at excess, which it just adds a new step, which is good, something new, right? And then we're going to look specifically at halogen and alkali metal reactions, alkali metal combination reactions with oxygen, and also alkali metal with water. The one with water is going to look like kind of single displacement. It's very familiar, I think, but the other two might be slightly new, those two combination reactions, but we'll get there. Now, combustion reactions are also covered in this chapter. Again, I feel like the layout of these chapters is a little weird. Like we do two types of equations in chapter 4, but then we don't do the rest until later chapters. I don't know, it's kind of interesting. Normally, most textbooks, they do all the reactions in the same chapter, or at least most of them. But whatever, we'll do it piece by piece. For this one, we're starting with combustion reactions. And so hopefully this one does look familiar. With combustion reactions, combustion burning, right? But we're going to specifically look at a hydrocarbon. So I just picked C3H8, which is propane, or if we were using our nomenclature, it would be tricarbon octahydride. And we're going to take that propane and whatever hydrocarbon it is for that matter, we need the oxygen for the fuel for fire, right? For this combustion reaction to occur, you have to have oxygen. And in all of your combustion reactions, you get the same two products in a perfect world. So we always make this assumption that we have complete, perfect combustion. We're not getting any bad side products like carbon monoxide, which of course you worry about. It's been on the news lately because it's been so cold and people might be running space heaters. And if you can always run the risk if it's in a closed space, if it's doing any kind of combustion reaction, that instead of producing CO2, you produce carbon monoxide. And unfortunately, it's odorless and it just makes you sleepy, right? And so you go to sleep and then it does worse things than that, right? So unfortunately, sometimes you take a nap and you don't wake up. So always when you're doing a combustion reaction, make sure it's outside. So in the hurricane season, they talk about that with generators. In cold season, they talk about it with space heaters, if your space heater is using some kind of combustion reaction. But anyway, so we've got this C3H8 propane. You're always going to have oxygen as the second reactant in a combustion reaction. And like we may have seen in those combustion analysis questions back in chapter 3, when, yeah, I just turned my heater on and realized it doesn't work. So thankfully I have a gas stove. So I just like put a pot of water on the stove and turned that on and that heated up the whole house. So that worked really well for me. And I'm not going to call someone to fix my heater because I think we're probably done with it by now. And I don't really mind the cold. I prefer it warm though. I think I'm getting older. Anyway, that's an aside. So in a perfect world, all of the carbon comes out as CO2, carbon dioxide, and all of the hydrogen comes out as water, but it's going to be in the gas phase because combustion reactions always have heat. And we'll see that triangle symbol more when we get into thermo. And chapter 4, this chapter is included on the first test. So that's a good question. So the first test, we have a lot of content. I always tell students with Chem 1 that your first test is almost like your final exam for intro. It won't have double displacement reactions on there, but it has a lot of everything else, right? So nomenclature is a big one. Stoichiometry today is a big one. Mass moles, molecules, empirical molecular formula, percent composition, atomic structure. I mean, there is a lot on this first test. So that is sort of the struggle with Chem 1 is that a lot of the content looks the same. And I tell my students that you sometimes can take it for granted because you're like, oh, this seems pretty familiar. I don't really have to study this because I already learned this. But I think when you get that much content thrown at you for one test, it can maybe be a little overwhelming. And so sometimes the first test scores are not as good as they should be, just because I know my students usually for Chem 1, I know the level that they're used to performing at. And sometimes that first test, it's like, ooh, that hurt. That wasn't what I expected from what I had from intro, which is why I make a lot of students take the final exam for intro. Only if you have an A on all your tests do I let you exempt. That's really my reasoning why, is because studying for the final exam really does help you when you get into Chem 1 because you had to review all that content. Anyway, so this first test, which we are going to look at next week during the Zoom session, it does have quite a bit of content on there, chapters 1, 2, 3, and 4. Now for this fourth chapter, The combustion reactions, like we were just talking about, we've got the hydrocarbon always, right, in a perfect world produces carbon dioxide and H2O. Because it's hot, we're burning, right? The H2O is going to be in the gas phase as well as the CO2. Now, when I go to balance this equation, and you'll have some kind of, generic balancing in the chapter, but usually with balancing equations, unless we have a specific type of reaction, there's not really a perfect place to start that I can say, yeah, always start with this and it'll always work. But what I can tell you is if you have an element or in this case, O2, a molecule, but it starts out in one place on one side of the reaction equation, but then it splits into two or more places on the other side of the equation, I always do those at the very end. Now, carbon is going to be easy. It comes from one spot, it goes to one spot. That'll be easy to balance. Hydrogen, same thing. So because the oxygen splits on the product side, I'm going to save that one for the end. I'm going to get the carbon and the hydrogen done first, and then I'll do the oxygen at the very end. So the carbon's pretty straightforward. I've got 3 carbons in the propane. When I come over to the product side, I have to have 3 carbons, right? So I'm going to put a 3 in front of the carbon dioxide. So there's my 3 carbons. I've got 8 hydrogens in the propane on the reactant side. I need the multiple of 2 on the product side to get me to 8. So I'm going to put a 4 in front of the water. And then now that my product side is hopefully balanced, I'm going to sum the oxygens. So in that carbon dioxide, I've got a coefficient of 3 times a subscript of 2. So I have a total of 6 oxygens in the CO2. And then for the water, I've got a coefficient of 4 and a subscript of 1 on the oxygen. So 4 times 1 is 4. So 4 oxygens in the water molecules, 6 in those 3 carbon dioxides. So I have a total of 10 oxygens on the product side. So to balance that on the reactant side, I need the multiple of 2 to get me to 10. So I'm going to put a 5 in front of the O2. And so now I've got a balanced combustion equation. So the combustion equation, I think it's fairly straightforward to me. I always was like, yeah, this is one of the easier ones, because as long as you remember the 2 products, the CO2 and the H2O, then really everything else flows pretty nicely. Just balance oxygen at the end, do carbon and hydrogen first, and then it's pretty straightforward. But that's the big thing with combustion reactions is you have to remember, again, in a perfect world, perfect combustion, we're not worried about carbon monoxide poisoning or anything like that. Always make sure on the product side that you produce the CO2 and the H2O. All right. And also always know with a combustion reaction that your oxygen, the O2, is always the second reactant. So if the question says you're doing a combustion of propane and that's all it says, predict the products and balance, make sure that when you say, okay, it's combustion, you have that propane, but it's always reacting with O2. All right. So always produce CO2 and H2O, and always your O2 is a reactant in a combustion reaction. All right. Now that we have the balanced equation, let's do some stoichiometry. So this first one I think is going to look really familiar. It says what mass of carbon dioxide can be made from 125 grams of propane. And so we saw this in chapter 3, that if we have the mass of a substance, our first job is always, when it comes to stoichiometry, it's always go to moles first, always. And so y'all remember that. And then the only question is, what conversion do I need? And I'm going to grab that first. If I have a mass, right, if you're ever given a mass, your bridge to moles is molecular weight or molar mass or formula mass or whatever you want to call it. All right, but I'm going to go to the periodic table and I'm going to get 3 carbons at 12.01 a piece, and I'm going to do 8 hydrogens at 1.01 a piece, and I get a molecular weight or a molar mass of 44.1 grams per mole. All right, and just as a quick aside, I did look at those chapter 3 quizzes. Your molecular weight and my molecular weight, if it's pretty close, that last digit is off by maybe a couple, I'm gonna fix it. Just give me until late tomorrow to get all the quizzes regraded. Because like if you put 1.008 for hydrogen and then round it to 2 decimal places at the end, obviously that's fine. You know how to do it. But if I use 1.01, my last digit there is going to be a little bit different than yours, but it's certainly reasonable, right? So just give me some time to get it fixed. All right, so I've got the molecular weight of the propane. Now the next thing it says is it wants to know the mass of CO2. And so again, if I'm looking for mass or I'm given mass, I know it's just like automatic. I need to get the molecular weight from the periodic table. So I'm going to need the molecular weight or molar mass of carbon dioxide. All right, and if I add up a carbon, 12.01, and then 2 oxygens, right, 16 and 16, I get a molar mass, and I'll put that, I can fit it over here. Yep, so my molecular weight of CO2 is 44.01 grams per mole, not to be confused with 44.11. All right, so we'll have to keep those straight. So with any stoichiometry or unit conversion type question, you always start with what you're given. That is our measurement, and yet I wrote the wrong substance, sorry. C3H8, 125 grams of C3H8. And when we do our unit conversions, we obviously know we want grams to cancel out on the bottom. And as we talked about, you always go to moles first. So how do I get from grams of C3H8 to moles of C3H8? And of course, that's the molecular weight or molar mass from the periodic table. So when I added up the 3 carbons and the 8 hydrogens from the periodic table, that's where I got 44.11 grams per mole. So that got me grams to moles. So I now know how many moles of propane I have. When I look at the balanced equation, what I can tell by those coefficients in front, and if there's nothing in front, it's an implied 1. For every 1 mole of propane I react, I produce 3 moles of CO2. So I'm comparing those 2 substances in the equation because that's, of course, what the question is asking me to compare. Now I can compare any 2 things that I want, but in this question, I'm focusing on the propane and the CO2. So always the substance you're starting with is going to go on the bottom. So we're going to get rid of the propane on the bottom. And what we're being asked about, the CO2, goes on top. And so when you have a conversion step, only one thing can change at a time. If in this first conversion step, I changed the unit, I went from grams to moles, but the substance stayed the same. We were just looking at propane in that conversion step. In the next conversion step, I'm changing substances, which means my unit has to stay the same. And the only way you can have 2 different substances in a conversion step is if the unit is mole and mole, right? That's the mole ratio. That's how we compare any 2 substances, is from the balanced equation. So we grab those coefficients. The equation says for every 1 mole of propane, I'm going to produce 3 moles of CO2. So that's called the mole ratio from the balanced equation. Now, the last conversion step here, I want to get rid of moles of CO2 and I want to get to grams. And this is where I sometimes will see a little bit of a detour because student knows to go to the periodic table, right, for mass, and they add up a carbon and 2 oxygens like we did. But then they get thrown by that coefficient in front, the 3. And they think, well, if there's 3 of them, don't I need to multiply that by 3, the 44.01? And the answer is no. Like, everything has its place, right? So when we do a molar mass from the periodic table, it's always based on 1 mole. When we have that coefficient of 3, that 3-to-1 ratio from the balanced equation, that only factors in that center mole ratio step, right? Once we have factored in that 1-to-3 ratio, we're done. We don't have to consider it again. So when you're looking for the molecular weight or the molar mass of a substance, never include the coefficient, just the formula. So 1 carbon, 2 oxygens. The coefficient only comes in the mole ratio step. So when I go to get my molar mass or molecular weight, again, whatever you want to call it, of the carbon dioxide, that's where I added up 1 carbon, 12.01, oxygen, 16.00, and then another oxygen, 16.00. That's how I got 44.01 for the molecular weight of the CO2. So on my calculator, I'm going to take 125 divided by 44.11 times 3 times 44.01, and I'll keep my 3 significant figures. And I'll put my answer over here. I get 374 grams of CO2. So that would be the mass of carbon dioxide I could produce from the 125 grams of propane. And obviously that means that we're adding mass of oxygen, because if you looked at that and you said, wait a minute, how can 125 grams produce 374 grams? Well, it has to be picking up quite a bit of mass of oxygen along the way. All right, but you take your mass, right? Go to moles first, divide by molecular weight or molar mass from the periodic table. Include the mole to mole ratio. That is always your center step of every stoichiometric calculation you ever do. And stoichiometry means we're comparing 2 different substances in a balanced equation. And then since we want mass of CO2, again, that means we need molar mass or molecular weight. All right, now the next question, we're going to use the same equation, but we're going to change it a little bit. We're still going to look for mass of CO2, But now we want to know what mass of CO2 could be made from 1.26 times 10 to the 24 molecules of C3H8. And what I wanted to emphasize here is that when we have molecules, right, we don't need molecular weight. Instead, the conversion is going to be different. We only need molecular weight if we're canceling out grams, right? And you saw this in chapter 3. If we want molecules or we have molecules, then of course our conversion is Avogadro's number. So I'm going to start with what I'm given, 1.26 times 10 to the 24th molecules. MOLEC is the abbreviation for molecule of C3H8. We still go to moles first. That doesn't ever change. If in doubt, always go to the moles first. But what changes here is that conversion, right? In order to get to moles, we know that we need to cancel out molecules, and that conversion is Avogadro's, 6.022 times 10 to the 23rd. All right. Now, in the next conversion, now it's going to look the same as what we did in part A above in that previous example. The mole ratio is always the center step. So we're going to get rid of moles of C3H8 on the bottom. Again, we're going to CO2. The equation hasn't changed, right? So it's still a 3-to-1 balanced equation. And then since we want we want mass of CO2, we need the same molecular weight of 44.01 grams per mole of CO2. So I wanted to do those two examples kind of side by side just to show you that if you want grams, right, your conversion step, right, is always going to be the same. If we're looking for mass of CO2 at the end, we need the molecular weight at the end. In the center of every stoichiometric step is always that multimole ratio. And we know we're doing stoichiometry because we're comparing two different substances in the balanced equation. So you know that's always your pass through. And then the other thing was, okay, if we're given mass, then again, molecular weight or molar mass is the conversion to get to moles. If we're given particles, then instead we use Avogadro's. But overall, the system is pretty much the same. Whatever you start with, go to moles first, do your multimole ratio, and then get wherever you need to go, right? If you need mass, then molar mass. If you needed molecules, you'd use Avogadro's. All right, so on the calculator, I'm going to just real quick take the 1.26 times 10 to the 24th divide by 6.022. I use the EE, right? EE key 23rd, then multiply by 3, and then multiply by 44.01. And we're still dealing with 3 significant figures here. So the answer I get is 276 grams of CO2. All right. Now for both of those questions, what we had was one starting material and looking at one product. And if I slide that back down just really quick and look at the equation, there was a second reactant here, oxygen, right? But since in both of those questions, oxygen was never mentioned, then we just assume it's present in excess. And this reaction will go and go and go until that propane runs out. So we were figuring out how much CO2 can we make from this starting amount of propane. Again, that calculation assumes that we have plenty of oxygen to make that work, but the reaction will stop when the propane stops. But of course, we can complicate that. And we can say, okay, well, what if I take 125 grams of propane and react it with 575 grams of oxygen? Now, instead of looking for CO2, I'm going to ask just kind of a basic question, although it's not really that basic. I'm going to say, excuse me, what is the limiting reactant? In other words, which of those reactants limits how far the reaction can go and runs out first? Now, in this question, and I have to say, I don't ask questions this way. I don't know why. I just prefer to just always go to an endpoint, like what mass of CO2 or what volume of water or how many particles of water or whatever. That's usually my way. I like a clear endpoint. If it's just going to ask you what the limiting reactant is, and I will say that this is going to help us when we do excess reactant here in just a minute. When you're asked for the limiting reactant and that's it, it's kind of a little bit harder, I think, for students because you don't have that clearly defined endpoint like grams of CO2, right? So the way that I think about this, and again, this is just the way my brain thinks about it, is I'm going to take my first reactant, all right, in this case, the propane, and I'm going to determine how many reaction cycles, that's the way I think about it, how many reaction cycles could it do before it runs out. Then I take the second reactant in this case, the oxygen, and I answer the same question. How many cycles, how many reaction cycles could it do before it runs out? And so even though it doesn't ask you a clear endpoint like mass of CO2 produced, we're going to still make our clear endpoint. We have to make sure you compare apples with apples, right? It's kind of a cliche, but make sure that you take this mass of propane and the mass of oxygen and get them both to the same endpoint. Technically, you could pick whatever endpoint you want, but you have to get them both to the same thing. And what I mean by that is at this point, these two numbers are not comparable. You have a mass of propane, you have a mass of oxygen. And they're not comparable because they're different substances. That means the molar mass is going to be different. And in the balanced equation, they have different molar coefficients. So it's not even a 1-to-1 ratio. Like for every 1 propane in the reaction, you use 5 oxygen. That means you have to have 5 times as many oxygen moles as you do the propane. So there's those two numbers, right? The mass of oxygen and the mass of propane, they're not comparable. So we have to make them comparable. So I'm going to start with my first reactant. I have 125 grams of propane C3H8. Now, just as we talked about earlier, it is a mass. Your first job is to always go to moles. That never changes. And so we're going to need that molar mass or molecular weight, whatever you want to call it, from the periodic table. And we saw that one earlier. It was 44.11 grams per mole. All right, now this is where it might get a little weird. Now, instead of going to a clear B, right, like to this other substance on the product side, instead what I'm going to do is I'm going to just look at one reaction cycle. Basically, I'm going to look at the balanced equation. So when I go back up to my balanced equation, sorry to keep moving this, when I look at my balanced equation, every time I go through one reaction cycle, I need 1 mole of propane. So that's what I'm going to put here. For every cycle, I need 1 mole of C3H8. Now, cycle, I'm going to put a little asterisk there. It's not really a unit, right? But I like having some kind of unit because I like to see my work and I like to follow it through and kind of know what everything means. So I would write this as, okay, I got 2.83 cycles. But again, cycles, I put a little asterisk by it because it's not really a unit, not like grams or molecules. And you're going to be asked a question like this on the practice quiz in chapter 4. And the system, Dr. Musgrave, he doesn't put a unit in when he made some of these questions. And if you put the unit in, the system's going to say, well, that's not right, because Dr. Musgrave doesn't use cycles. And I like to use cycles, but preferably for the system, you're just going to put a 1 on top. So yeah, that answers your question. But I always like having a unit. I don't know. I guess my teacher was like, always include your units. So I just always like having a unit, but technically it's not really a unit like grams or moles or molecules. So the system's going to expect you to just put a 1 on top. If you put cycle in, the system will mark you wrong, but I'm going to go in and fix it. All right. Okay, so that's how many cycles I could go through with that mass of propane. Now, the next question is, well, how many cycles could I do with the mass of oxygen, right? So now I have to start with my second reactant. I have 575 grams of oxygen. Your first job, always the same, go to moles, right? So let me scooch that up just a little bit. So for, 1 mole of O2 going to my periodic table, again, looking for molar mass. Oxygen is 16, but I take it twice because this is a subscript, so 32.00 grams per mole. And then for each cycle, again, cycle, you could leave that off. And then I'm going to look at moles of O2. So I go back up to my balanced equation and I say, okay, every time this reaction cycles, how many moles of O2 do I need? And that coefficient says I need 5. So I'm going to go back down into my setup and say, okay, for every cycle, I need 5 moles of O2. So I'll take 575, divide by 32, and then divide that by 5, and I get 3.59 cycles. And again, cycles not really a unit. So basically the idea is the propane could go through almost 3 cycles before it stops and runs out. The oxygen could keep going, but the oxygen can't keep going if there's no propane to keep going with, right? So at this point, you have determined your limiting reactant. Whichever one produces the smaller amount is your limiting reactant. So the 2.83 is really not It's not really anything you can use in terms of it's not a mass of something, it's not a molecules or something, right? It's only helping us identify that the propane reactant runs out first. Once it goes through that 2.83 cycles, it's gone. And so the reaction has to come to a stop at that point. So this is one way to determine your limiting reactant. So C3H8 is the limiting reactant. So if we did want to follow this up and then say, okay, well then how much CO2 could we make? We're going to know that the propane is going to determine that because the oxygen will be present in excess. All right, we'll get to that in the next example. And the oxygen, it can't go all the way through to make the CO2 on the product side because it doesn't have enough propane to do that with. The propane limits how far this can go and thus limits how much CO2 we could make. So if your propane is the limiting reactant, then your other reactant, in this case, the O2, is going to be present in excess, right? We're not going to use all of it. We're going to use quite a bit of it, right? If you imagine the percentage 2.83 out of 3.59 cycles, we're going to use a pretty good amount of it, but not all of it. There will be some that's left over. And that's what's going to be the new question for Chem 1. We didn't look at that with intro. With intro, we just looked at limiting. We didn't think about excess. Now we're going to look at excess. So we can add a little bit to this, all right? So that's the first couple of examples. Hopefully so far, most of that seems pretty familiar. On the next page, I've got another example for us to work through, another combustion equation. So let me keep that where it is. And of course, my videos froze really quick. That's okay. That'll give you a moment to catch up and write, I guess. There we go. All right, so now I've got a second combustion reaction. I've got butane, C4H10, again, reacting with O2. So when you see this, right, you know your two products are going to be CO2 and H2O, both in the gas phase. All right, and then, excuse me, I'm working on a little bit of a tiny cold. Nothing bad, just a little bit, nothing, no, like, I mean, it's an easy cold. I haven't lost any sense of taste or smell. That's the worst part of a cold, in my opinion. So I got 4 carbons in the butane. There's 1 in the CO2, so we're going to multiply by a 4. I got 10 hydrogens in the butane. Multiple of 2 to get me to 10 would mean I put a 5 in front of the water. And now when I sum the oxygens, whenever you have an odd number in front of water, you're going to get an odd number of oxygens. So you have a choice here. When I look at my oxygens, 4 times 2 means I have 8 in the carbon dioxide, plus another 5 in the water, means I have 13 oxygens total on the product side. If I want to balance that on the reactant side, I need the multiple of 2 to get me to 13. And since that's not a whole number, I have a choice. I can leave it as a fraction, 13 over 2, or I could do a decimal. I could do 6.5 if you want. I know when I first started doing these, and it's been a while, I don't know, 30 years or whatever, I only saw fractions, but now I see books doing decimal form as well, like 6.5. So it doesn't really matter. But if we are going to do a mole ratio, like we would up in like the previous example that we did, we may prefer to have whole numbers. So if you do prefer to have a whole number, then all you would do is just start over and multiply everything by 2. So it would be 2C4H10, 2 butanes. We'll leave the oxygen blank. We'll come back. And now instead of 4 carbon dioxides, we'll have 8 on the product side. And instead of 5 waters, we'll have 10. So we just multiplied everything through by 2. Now when I go to sum the oxygens, 8 times 2 is 16, plus another 10 in the water means I have 26 oxygens on the product side. The multiple of 2 to get me to 26 means I put a 13 in front of O2 on the reactant side. To me, those two equations are exactly the same. It's just one doesn't have a fraction and the other one does. And to me, that's up to you which one you're more comfortable with because they're going to work the same way. All right, excuse me. I hope I covered the mic well enough when I coughed. So now this question says, what mass of the excess reactant is remaining after 275 grams of the butane reacts with 1,175 grams of the oxygen? All right, so what's a little bit more challenging about this one is if we're looking for the mass of the excess reactant, that means we need to know which reactant is limiting or which one's excess, right? We need to know which reactant we're even talking about. So again, this is a little bit of a harder question because the endpoint is not clearly defined, right? I know that I'm either looking for mass of butane or mass of O2 because I know I'm looking for a reactant mass. So it's got to be one of those two. But specifically, I need to know which of those reactants is the excess, which one is present in excess. And I know you want to look at those two numbers and say, 275 is way less than 1,175. So I'm just going to assume that the butane is excess. You really can't make that assumption because, again, the molar masses are totally different. And you can see this, I need 13 moles of O2 for every 2 moles of butane. So 6.5 times as much moles of O2 as I do butane. So you can't just look at those two numbers and say, oh, well, it's obvious that that one's going to be limiting. All right, so there are different ways to do this, but this is typically the way that I'm going to do it. What I kind of do here, and sometimes you get lucky, sometimes you don't, is I'll take my butane and I will figure out how much O2 I need to make that reaction work at 100%. Now, that's not necessarily the best way to do it. The best way probably is to just take the time and figure out which one is limiting first, right? Because otherwise you may get confused and have to do calculate a different calculation. So you do the first, like if I take my butane and figure out how much O2 I need, and that number is bigger than 1175, then that's going to tell me that O2 was limiting, and I'll have to do the other calculation. Okay, if O2 is limiting, then how much butane would I react? So because I think that's probably more confusing, even though that's the way I always did it, I'm going to show you what I think is the way that will always work. Okay, so first, figure out which one is your limiting reactant. Just like we did with the last example, right? So again, we're not doing like a grams of CO2, we're just figuring out which one is limiting. So I have 275 grams of the butane, the C4H10. I know I always go to moles first. All right, and then I need my molar mass. Sorry for squeezing that in. So 4 carbons at 12.01 a piece, 10 hydrogens at 1.01 a piece. I get 58.14 grams. So again, that's the molar mass, molecular weight, whatever you want to call it. Then for one reaction cycle, if I look at my balanced equation, I need 2 moles of C4H10. So if I take the 275, sorry, divide by 58.14, and then divide that by 2, I get 2.36 cycles. All right, and again, cycles not really a unit. All right, now I start with my second reactant, 1175 grams of O2. 1 mole of O2 has a molar mass or a molecular weight of 32.00 grams. For every 1 reaction cycle, I need 13 moles of O2. All right, using that balanced equation that we came up with the whole numbers. So 1175 divide by 32, divide by 13. All right, I get 2.82 cycles. All right, I'm just going to type it in one more time. I always get a little paranoid that I went too quick. All right, yeah, 2.82 cycles. All right, so you can see the 1175, even though it was such a much larger mass, we're going to end up using most of it, but not all of it. So what we can tell then is that 2.36 obviously was smaller than 2.82. So that tells me that C4H10 is my limiting reactant. It's going to tell me how far the reaction can go. And then that tells me that the O2 is the excess reactant, right? Because if one's limiting, the other one is excess. So now I can go back up to the question. And when it says, what is the mass of the excess reactant? Now what I know it's really asking me is for the excess O2, right? The excess mass of O2 that I didn't use. Okay, so we are a step closer. In order for me to figure out what mass of O2 I used, I have to start with my limiting reactant. So I'm going to start with my butane, because again, that's going to tell me how far this reaction goes. You always start with the limiting reactant and first figure out how much oxygen I will use. So I'm starting with that 275 grams of butane. Knowing that that's my limiting reactant, what mass of oxygen am I going to consume to react with that 275 grams of butane? All right, so now the second part here is, let's determine, I'm trying to write this so it's clear, determine the mass used of the excess reactant based on the limiting reactant. So in other words, start with your limiting reactant and convert that to the second reactant. So I'm going to start with my 275 grams of the butane. Again, that was my limiting. That's going to limit how far this can go. The molar mass is the same. 1 mole of butane was 58.14 grams. Now I have a clear B, right? Now I know exactly where I'm going. I'm going to convert the moles of the butane to moles of O2. Because now I know when it said the mass of excess reactant, what mass? The excess reactant, that was code for O2. I figured that out. So I go back up to my equation. I've got my balanced coefficients, right? 2 to 13 is my ratio. So 2 moles of butane for 13 moles of O2. And then to get to mass, we need molecular weight from the periodic table, 32.00 grams. So if I take my 275, divide by 58.14, times 13, divide by 2, and then times 32, and keeping 3 sig figs, 984 grams of O2 would be used, right? That's how much I would need to react with that mass of butane, the 275 grams. We're still not done, right? Now, if I go back and read the question, it's very clear. It says, what mass of the excess reactant is remaining after these two have done their reaction? So what I understand here is when I look at my balanced equation again, all right, so to me, I always like writing things out. All right, so let me just write the balanced equation really quick here again. We started, so here's at the start. We started with 275 grams of the butane. And the question said we started with 1175 grams of O2. When we are done, right, at the end, we have used, actually, let me do it this way. What did we use, right? Well, with the limiting reactant, we used all of it, right? So we know that there isn't any left, right? Because that is the thing with the limiting reactant. You use all of it. All right. Now, with the oxygen, based on my stoichiometry, if I had 275 grams of the butane, I used 984 grams of the oxygen. That's what my stoichiometry told me. So if I take a difference in those two numbers, 1175 minus 984, I have 191 grams of the O2 left. And so that's really what the question is looking for. After all that, it only took a page, right? So when the question said what mass of excess reactant was left, that's what we were looking for here. That's the mass that was left. So I'm going up to I'm reading a question in the chat. The cycles of A, the only thing you have to be careful with when you're back up here with the cycles, right? When you determine, that's a really good question, Sammy. Here's what I want to make sure, and I hope I do this in a clear way. When you're back up here and you determine, aha, this one is my limiting, right? The 2.36. And you say, okay, if this is my limiting, I know oxygen is excess. I'm just going to take this and multiply it by the O2 molar mass. The thing that you didn't capture is the 13, right? Because that mole to mole ratio, if you look at comparing these two right here, where we're finding limiting reactant and we're actually doing the stoichiometry, when I factored in the cycles, I took care of that 2 coefficient for the butane, but that 13 coefficient for the mole ratio for the O2 isn't included. So if you want to take that number of cycles and say, okay, obviously I need to go to O2, don't forget, multiply by the coefficient of O2 and the molar mass of O2. Hopefully that makes sense. I usually don't recommend doing it that way because what I'll find is most students will forget the 13. They'll just do the molar mass step and they forgot the 13. And then they look at the number and they're like, wait, this can't be right because they lost that 13 factor and the numbers look way wrong. So that's why I usually say, you know what, this is familiar. Mass of A to moles of B to mass of B. So that's why I usually just start over. But a lot of times students want to do that. They say, okay, well, I figured out my limiting reactant. I'll just pick up from there and go to my B. If you do that, just make sure you capture the moles of B as well, because that's not in this step. All right. I hope that made sense the way that I said it. Okay. So this was step 3, kind of going 1, 2, and 3. Okay, good. All right. So this is, again, kind of the little process. We started with 275 grams of the butane and 1175 grams of oxygen. What we first figured out, if I kind of go back, is we figured out which one was limiting. All right. And that was using the same scenario we did in the previous page. So we found out butane, slightly less cycles, right? So butane is going to be less. Now from here, honestly, there's a lot of math you could do. Some students can look at this and say, well, 2.36 as a percentage of 2.82 is blank. And then that percentage times 1175 would be what's used. You know what I mean? Like you could do it that way. There are different ways to do it. But I try to be as consistent as possible with the stoichiometry. So we found out butane limiting. So we know to start with our limiting, right? Always when you do stoichiometry with a limiting reactant problem, always start with whatever your limiting reactant is, what you just identified. And now we're going to use that to determine how much of that second reactant we actually used. So based on our stoichiometry, the 275 grams of butane should have used or reacted with 984 grams of oxygen. Since we started with 1175 grams, if I only used 984, that means we had 191 grams of oxygen left over, right? And that's really what the question was looking for. So a lot of work for one question, no doubt. But again, kind of taking intro and amping it up a little bit. Like it's nothing is too unfamiliar. We're just adding another step to it, right? And that makes it a little bit longer. All right, so hopefully that was explained fairly well. Now let's look at another question on the next page. All right, so the 2 types of equations that we've got for this first test, and they're all in chapter 4, they are all under the umbrella of redox, but we are not looking at them as redox problems, which is kind of nice. We dive in deep in redox and Chem 2, not so much in Chem 1. So we have in this first test, the combustion reactions, like we've already talked about, always make CO2 and water. Oxygen's always the second reactant, balancing that out. The second type of reaction we have are all including alkali metals. So for all of the rest of the examples I have for today, I just use sodium, but just know that instead of sodium, you could use any alkali metal. And honestly, it works with the alkaline earth metals too. They're the same, they're highly reactive. The only difference is obviously the charge will be different at the end for the cation, right? We know alkali metals are always +1, alkaline earth metals are always +2, but they do the same types of redox reactions with oxygen and halogens and water. So for all of my examples, I'm just using sodium because that's, just an easy one to use. Okay, so first question says, sodium metal reacts with bromine gas to make solid sodium bromide. All right, so that doesn't sound too bad. This is like a nomenclature thing. The only thing we have to remember is Hofbrinkel. All right, so in Intro Chem, we learned that there are 7 elements that when we are talking about them in their elemental form, so not as ions, not as compounds, right, but just in their elemental form, like bromine, right, they're going to be diatomic. And that looks familiar from the last page when we were talking about oxygen, right? Oxygen is O2, not just O, but O2. So that's one that we're really familiar with. All right, and you'll see oxygen is one of the 7. Now, for me, when I learned these, I thought it looked like it made a 7 on the periodic table. So that's what I thought made it look easy to remember. And I hadn't heard of Hofbrinkel. My teacher didn't give me that. So you have H, N, O, F, and then down the halogens, chlorine, bromine, and iodine. So that's how I remembered it. I was like, oh, it makes a 7. But Hofbrinkel does make it a lot easier. So with those 7 elements, when we're talking about their elemental form, right, we want to always do diatomic. So when the equation is talking about sodium metal, sodium is not one of the 7, right? It's not part of Hofbrinkel. So we just write Na. Metal means we're going to put state of solid on there. When it says it reacts with bromine, right? Not bromide, not bromine in a compound, just elemental bromine. That's where we're going to put the Br2. All right, it says it's a gas, so I'm going to put gas. On the product side, it tells me it makes sodium bromide, but I really don't have to have that information. Here's why. What I can tell here is I've got two elements. And so what has to be happening is the compound is being formed. If we know if it's a chemical reaction, bonds are broken, new bonds are formed, that kind of thing. And if you have two elements, right, the only possibility is that you have a combination reaction. So sodium, I know as an alkali metal is a +1. Bromine as a halogen is -1. And so I know sodium bromide should be +1, -1. Now, inevitably, somebody says, wait a minute, didn't you say bromine is a 2, like Br2? Here's what's happening. This is a redox problem. The sodium starts out in its elemental form, not as an ion, has all of its electrons. The bromine, the Br2, same thing. It's in its elemental form. It's not an ion. And what happens is the sodium gives an electron to bromine to become the sodium cation. The bromine takes in the electron to become bromide, right? That's why we change the ending to IDE, is to distinguish between bromine and bromide. So bromine is 0 charge. Bromide is the ion with a -1 charge, right? And it's the bromine that is the diatomic. The bromide, the ion, it's only diatomic if that's what you need to balance out charges. But because we are now in an ionic compound, we just look at those charges to balance them out. Sodium +1, alkali metal, bromide -1, halogen +1, -1. That's why it's just NaBr and not NaBr2. All right, so that bromine Br2, that bond between them, that gets broken. And then a sodium gives its electron to bromine to become sodium bromide. And of course, if you look at that, you're like, well, wait, there's 2 bromines. You're right. So there has to be 2 bromines on the product side, which means there's going to be 2 sodiums on the reactant side. All right, now if you can picture Lewis structures in your head from intro chem, that's fantastic, right? You think about sodium having 1 valence electron and bromine with its 7 valence electrons. And you can see how that sodium is going to donate that electron, right? If you are like, wait a minute, I don't remember that, then just forget I said anything. Don't worry about it. But that's why each bromine, right, needs 1 electron to become bromide, and sodium has that 1 electron to give. So if I've got 2 bromines here, I need 2 sodiums to make 2 sodium bromides. And the state here, this one's going to be a solid. A question tells us so. So we have a nice balanced combination reaction. And again, you could substitute potassium, lithium, cesium. It would all work the same. Same with the halogen. It could be fluorine, chlorine, bromine, iodine, right? All of the halogens, it would work exactly the same. All right, so we've got a balanced equation. Now we can continue. What is the percent yield if 25.0 grams of sodium reacts with 85.0 grams of bromine to produce 75.2 grams of NaBr? Okay, so these questions I think were like kind of the hardest that we got in intro chem, because if you look at it, we've got not 1, not 2, but 3 numbers that are given to you. And sometimes just organizing that in your head can be challenging, right? Piecing that together and figuring out, what do I start with? Where do I go? So here's what I always want to say. If percent yield is being asked for, right, we have a formula for percent yield, which we probably remember from intro. If you're determining percent yield, you need to know the actual yield of the experiment divided by the theoretical yield times 100. Percentage is always parts per 100. That formula should look familiar. All right. Now, with a percent yield, and I see the tutors sometimes explain this wrong, which never makes me happy. If it's a percent yield, it will always be for a product, right? It makes sense. If we're looking at a yield, not a consumption, right? Not how much did we consume, right? But how much did we produce? How much did we yield? So your percent yield is always going to be for the product when you're determining a percent yield. So when I look at my equation up here, the only product I have is NaBr, right? So I know I want to know the percent yield of NaBr. That means I need to know the actual yield of NaBr, and I need to know the theoretical yield of NaBr, period, right? You got to compare apples with apples, right? So when I see those 3 numbers that are given to me back in the problem, I know one of those has to be the actual yield of NaBr, because We're not in lab doing this, so we can't know what the actual yield was. That has to be given to us. So that 75.2 grams of NABR, this is going to be important because we're going to use that as our actual yield, right? The question is telling us that's how much we actually made. So when I go to determine my percent yield, I'll have the 75.2 of the actual yield divided by some theoretical yield, which I don't know what that is just yet. And then I got to put this up in the margin, sorry, times 100, right? Because percent is always times 100. All right, so now what does that tell me? If I look back at my question, the 75.2 grams of NABR is just to help me figure out the percent yield. It's my actual yield of NABR. It's how much I actually made. What I then need to figure out is, okay, in theory, what should I have made? And I have a mass of sodium reacting with the mass of bromine. And like we talked about earlier, if I have a mass of both of my reactants coming together to make this reaction happen, I have to figure out which one is limiting. I have to know, right, which one of those two, the sodium or the bromine, runs out first. So in this question, because I do have a clear endpoint, right, I need to know my theoretical mass of NABR. I'm going to go ahead and not go through the step-by-step of finding limiting first and then figuring out this is what I'm going to do. All right, I am going to take my sodium and determine my mass of NABR. Then I'm going to start over and take my bromine and determine my mass of NABR, and then figure out which one runs out first. All right, so this is a different way of doing it rather than what we did where you find the limiting first and then take it to B. But to me, I always felt like this was shorter. All right, so I'm going to start with my first reactant. I've got 25 grams of sodium. All right, what should look familiar? Molar mass from the periodic table, 22.99 grams per mole for sodium. Now my mole to mole ratio, and this is where sometimes it gets tricky because if you look back at the question, you got sodium, bromine, and sodium bromide, and you're like, I don't know which one I'm going to, right? Like, you know, you're going to get rid of moles of Na on the bottom. Question is, where are you going? And that's why I always try to emphasize, if you're looking for a yield, it's always the product. So you're always going to the product on top, right? And our product is the NABR. So that goes here. All right, my mole to mole ratio from the balanced equation. In this case, it's a 2 and a 2. All right, so even though those numbers cancel out, don't cancel them out, because if you're showing your work for me on the test, I need to know that you know what those numbers are. So write them as you see them. So 2 to 2 ratio. All right, now last up here, getting rid of moles of NABR, and we want grams because our actual yield was in grams, so we want that unit to match. So on my periodic table, 22.99 for sodium added to 79.90 for bromine, I get 102.89. All right, so 25 divided by 22.99 times 2 divided by 2 times 102.89. To keep 3 sig figs, I get 112 grams of NABR. All right, not quite done. Now I start with my bromine. I had 85 grams, 85.0 grams of the BR2. Now, when I look for the molar mass of that, make sure you take the bromine twice. So bromine atomic mass 79.9 taken twice is 159.80. Molar mass, 2 moles of NABR, because that's from the balanced equation. But then when I look at the bromine, coefficient of 1. So just 1 mole of bromine to make 2 moles of NABR. And then since we're going to the same place, that molar mass is going to be the same because that's a constant. So we can use that same 102.89. So 85.0 divided by 159.8 times 2 times 102.89, keeping 3 sig figs, I get 109 grams. All right, so we circle the smaller. That tells me that the bromine was my limiting reactant. We used almost all of the sodium, but we would have a little bit excess, right? So the bromine tells us how far we can go. That right there, the 109 that we just calculated, this is a theoretical yield, right? In theory, if everything's perfect, this is what we should get. It's not quite what we got, but if everything was perfect, that's what we should get. So that is our theoretical yield, right? Everything based on stoichiometry is always just theoretical. So that's going to go back up into my percent yield calculation, right? We figured out that we should have made 109 grams. Question tells us we only made 75.2. So 75.2 divided by 109 and then times 100, because you always want percentages, right? Parts per 100. Go ahead and keep your sig figs. We got 3 all the way through, so don't round to a whole number just because it's a percentage. And I get here 69.0%. So that would be my percent yield of this reaction based on starting with 25 grams of sodium and 85 grams of bromine. Based on those two starting materials, bromine runs out first. We only make 109 grams of sodium bromide. And then theoretically, 109 grams are made. Actually, we only got 75.2. That means we had a 69.0% yield. All right. I have one more question here to look at. We've talked about combustion. We did alkali metals with halogens. This one, I've got alkali metals with oxygen, and then I need to show you alkali metal with water. So I know I try to budget an hour and a half for this. I know if anybody has to go, though, I don't take any offense to it, but I'm going to keep going. And if you have to go, don't worry about it one bit. You can always watch the rest whenever you have a chance. All right. So next question says, again, I'm using sodium, but any alkali metal will do. Sodium metal reacts with oxygen. Again, oxygen, part of Hofbrinkel, so we need to make it as an O2. And we're going to make sodium oxide. So again, another combination reaction. It's going to be an ionic compound, so we got to think about our charges. Sodium's +1, oxygen is now oxide, so it's -2. We know that from the periodic table. That means my formula here has to be Na2O, right, to balance out my charges. Then to do my mass balance, because I had 2 oxygens on the reactant side, I need 2 on the product side. So I'm going to multiply sodium oxide by 2. And then the 2 coefficient times the subscript of 2 means I have 4 sodiums. So on the reactant side, I need to put a 4 in front of Na. And again, I could substitute potassium here or lithium, and it turns out exactly the same. Now, this question says, what is the percent yield if 51.2 grams of the sodium oxide is made from 50.0 grams of sodium reacting with excess oxygen? All right, so I've got 51.2 grams of sodium oxide. It told me that we have excess O2 here, and I'm looking for 50.0 grams of sodium. So the fact that this told me I have excess oxygen means this is not a limiting reactant problem, means I don't have to worry about the oxygen, which is great. This reaction is just going to keep going until the sodium runs out, because I could keep going with oxygen, but the sodium is going to run out first, right? Oxygen is excess, which means I don't have to worry about it. So the other thing here is I'm looking for percent yield again. Percent yield, like we saw in the last example, right? We know that we need actual over theoretical times 100. And we're always going to determine the percent yield of a product. So in this case, we know that we're looking for the sodium oxide on the product side. And we know that if we're doing a percent yield, the actual always has to be given. So I was very careful about this. A lot of times students want to look at the wording and say, oh, well, whatever's given first is the actual yield. Right. Well, that's true in this question, right? What is the percent yield if 51.2 grams is made? That mass of sodium oxide, that is my actual yield of product. But in the last example, right, just to contrast real quick, I put that actual yield at the end of the question. So you can't always assume the actual yield comes first. What you can always look for, though, is if it's a percent yield, the actual yield will be for the product. That's how you identify what's what, right? Sodium and bromine in the last example, those are reactants. We're not doing a percent yield of a reactant, right? The sodium bromide is the product. So that's how we know that that 75.2 was the mass actually made of sodium bromide. In this question, right, the sodium and the oxygen are the reactants. The sodium oxide is the product. So that 51.2, that is the mass of my product. And that's my actual mass, which means I need to know what my theoretical mass is. So that tells me what I'm trying to figure out first. So I've got my 50.0 grams of sodium. We're starting with that. We're going to go to moles first. So we need the molar mass of 22.99 from the periodic table. Next up is the mole ratio from the balanced equation. For every 4 moles of sodium, we're going to make 2 moles of sodium oxide. And then for every mole of sodium oxide, what mass do I have? So I would take the 22.99 twice for the sodium, add it to the oxygen, and I get 61.98 grams for the molar mass of sodium oxide. So when I take my 50, divide by 22.99, times 2 divided by 4, and then times 61.98, I get 67.4 grams of sodium oxide. All right, and that is my theoretical yield, right? In theory, that's what I should get. Question says we actually got 51.2. So when I go to do my percent yield, I'll take the 51.2, divide by 67.4. We now know what that theoretical yield is based on the calculation. And again, keep your 3 sig figs. All right, and so I get 76.0%. So that would be my percent yield of this particular question. So again, another combination reaction for us to know how to do for the test, added to some more stoichiometry. Percent yield is always for a product, and percent yield doesn't have to always mean that it's a limiting reactant problem. In this case, it wasn't. If you see something where it says this reactant is excess or it's not mentioned at all, then we don't have to worry about it, not a limiting reactant problem. But percent yield, always look for your product. That's always where you're headed if it's a percent yield question. All right, so in terms of the balancing equations or equations that you have to know how to predict and balance for the test, we did combustion. We did the alkali metal with halogen. We did the alkali metal with oxygen. The last one we have to look at is the alkali metal with water. All right, so next page, one more here, and then we're probably pretty good. Sodium metal reacts with water. All right, and what we form here is sodium hydroxide solution because of the water and hydrogen gas. All right, and let me just kind of write it as hydrogen to help us remember hydrogen, again, part of Hofbrinkel, so it has to be H2. All right, again, Hofbrinkel, the 7 diatomic elements. So hydrogen never appears just as H by itself, not in a compound, right? It has to be H2. All right, and so this is going to look kind of like single displacement did. The sodium and the hydrogen switch places, right? But you have to almost picture water as hydrogen bonded to an OH. That might help a little bit because then the sodium bonds with the anion, the hydroxide, and the hydrogen comes out in the elemental form. And if you remember single displacement, the neutral becomes the cation and the cation becomes the neutral. And if you don't remember that part, don't worry about it. You'll just remember that alkali metals in water, they always produce the hydroxide. That's why they're called alkali, because alkali means base, right? So these metals, they are very reactive. You put them in water, the water turns into hydroxide and it spits out hydrogen gas. So we saw bubbling with these types of reactions. Now for balancing, when you look at this one's a little deceiving at first because we talked about, okay, if anything splits like hydrogen does here, save that for the end. So if you look first, sodium 1 and 1, that looks good. Oxygen 1 and 1, so that looks good. So you look like everything's going well. And then with hydrogen, you've got 2 on the reactant side in the water, you've got 2 on the product side in the hydrogen, and then another 1 in the hydroxide. So you've got a total of 3 hydrogens on the product side, and you're thinking that's not going to balance, right? If I put a 3/2 or some kind of fraction to balance the hydrogen, then that's going to mess up the oxygen. So what we know is with the reactant side, we're looking for multiples of 2 for the total of hydrogen to make our lives easier. Since we already have 2 hydrogens in the hydrogen gas, I'm going to put a 2 in front of sodium hydroxide to give me 2 hydrogens there. So now I've got 2 plus 2, so 4 total hydrogens on the product side. So a 2 in front of the water will give me 4 hydrogens on the reactant side. That 2 in front of water also gives me 2 oxygens. That balances the 2 oxygens I have on the product side. The last thing I look at here is the sodium. There's 2 sodiums on the product side. So on the reactant side, I need a 2 in front of the sodium. All right, and again, this reaction would work with potassium, lithium, cesium, right? We'd get the same hydroxide and hydrogen on the product side. So that's the last type of equation that we have to look at for chapter 4. Chapter 4 is mostly stoichiometry, and then of course some of that equation writing. A lot of this is going to feel familiar from intro chem. I hope like everyone's got a really good handle on molar mass and Avogadro's number, mole ratios, limiting reactant. We did quite a bit in intro, percent yield, but of course the new topic was, okay, what about excess, right? So hopefully that'll get you in good shape for chapter 4. If you have any questions for me, obviously please reach out and let me know. But other than that, I think that's a good place for me to stop for today.